This is a ladder logic diagram for a misting pump system. This ladder logic diagram program is provided by Alan Bradley, and it is called the RS Logic Micro Starter Lite, and the name of the file is mtincrss. What we're going to do is go over the logic on this main ladder to main program diagram. We're not going to go into any depth into the controls and settings over here. Just explain to a degree this, we'll call it an electrical diagram internal to the MicroLogic controller. So this ladder diagram, this we'll call it electrical schematic, runs a pump package. This pump puts out high pressure water for a misting application. This logic diagram here has 29 lines of code in it. If I page down, we get down to the bottom, and there is line 29. We'll go back up to the top here. So what this program primarily does is start and stop a pump, monitor a pump, and shut down the pump if there is some alarm conditions. So in a more precisely or more in depth of what it does is here's a document that covers some of the things that we're going to go over. So this is broken down into 12 sections. And within these sections there is 4 set points we're going to cover, 3 of them being time delay and 1 being a system pressure setting. So as we go through the ladder diagram, we're going to come back to this document and somewhat check off these areas as we cover them. But we'll review them as a whole at first. So the first one is that there's going to be an input call to start the system. This call can either be through a programming interface, which we're really not going to see in this video, but the other one can be through the PC interface, or through a programming interface, which is what we're going to be looking at. The other one is through a PC interface, which we really are not going to see in this video. And the other one is through some override toggle switches, which is also part of the programming interface. Again, to start and stop the system, the initial call for mist. Once we have this initial call for mist, what happens is that we monitor the input water pressure. We monitor that pressure to make sure that there will be water at the input side of the pump. And if there is not, there's an associated time delay that lets it get there. And if it doesn't, after 5 seconds it actually will shut down the system, shut down the pump. If there is the incoming water supply and it's at the proper pressure above 10 psi, then we will energize an output solenoid. These are the particular zones that we have in this system that will release high pressure water to misting nozzles. So once we energize an output solenoid, we actually provide a start run signal to the VFD, variable frequency drive motor. This is a signal, a set of dry contacts within the microcontroller that close and actually energize or send a signal to the variable frequency drive to start and run. Since this motor varies its frequency or varies its speed, it has to have something that that modulates that, or that tells it where to run at. and that is a feedback from a pressure sensor, pressure transmitter in the high pressure side of the pump. That's here providing feedback to proper pressure is maintained by pump. It also does monitor the pressure, overall pressure as a whole, and if something happens to the pump or to the system where a large leak comes about, it will actually shut the pump down. And that setting is actually set at 120 psi right now. So that covers, let's see, varying the speed of the pump to maintain set point pressure, initiating pump shutdown if proper pressure is not maintained. Covers those. The other thing that this monitoring package does, this ladder diagram, is provide a value of the water flow through the system. There is a water sensor in there that monitors flow. There's also a water sensor in there that determines whether there is actual water in the pump panel itself, and it will shut the system down. And then last, there is a temperature sensor internal to this pump panel, just to monitor the internal temperature to see if it's in any adverse environments, and it is not tied to any shutdown circuit at this time. So what we're going to do is go back and forth between this ladder diagram and this list of what the ladder diagram accomplishes, and kind of check them off. So the first thing is the input call to start the system. Now if we look at the ladder diagram, we've got some toggle switches here, and we've got some solenoid valves here. And then if any of those are energized, it actually energizes what is called a call for mist here. This is a bit within the controller that actually will designate that there is a call for mist. The other two items in this diagram are the shutdown circuitry. So if we have some problems with the system, these are the normally closed contacts that will actually end the call for mist. And you'll see throughout this diagram, this logic diagram, that we have little notes also that kind of tell a little bit of what's going on. So as I go over this as an overview, we're going to be going back and forth and up and down throughout this ladder diagram. Now I'm not going to get into any detail, but I'm just going to show where some control is accomplished, and where the monitoring is accomplished, and how it might start and stop. The logic gets to be a little hairy, and it's quite difficult to explain how actually all the logic works. It's best to go over it as an overview, and then if we get to that point, it could be explained in more detail. So you see we've got a couple of toggle switches here. These are actually internal to the control package. Override toggle switches. And then we've got these solenoids. Solenoid 1, 2, 3, 4, 5, 6. And these are actually the zone solenoids. And these are designated as bits internal to the program. And this bit is where the actual PC interface or a programming interface, customer programming interface, can open and close these bits to give the customer some control. I should actually say it's a user interface. So there's another program that makes it easy for the customer to control the system, and these are the bits that get turned on and off to actually open up individual solenoids. Now let's move down here a little bit. Some of this is a little later on in the programming, but we're going to come down here to this Debounce timer on line 3. this debounce timer is really a on-time delay, or a start delay. It's just built in so if something happens to the program, it just doesn't short cycle and start and stop and start and stop and start and stop. So that is set at 3 seconds here. That's what this preset means. Time base is 1 second. Preset is times out in 3 seconds, and that's an accumulated value. But you can see this debounce timer is tied into that call for mist. The call for mist goes back to line 1 when we actually make a call, and that energizes the debounce timer. Once that timer is energized, we actually have an input pressure sensor here, and this senses there's a pressure transducer on the input line, and that is set at, what is it? It's set at 10 psi. Actually, it might be set at 12 psi. And then this is the source of where it's at. No, this is the source, 12 psi, and it's actually set at 10 psi. So the last time I was running it, the actual incoming water pressure was 12 psi. And that's the input sensor. This debounce timer is closed, and this is an on delay of 5 seconds. So this is the timer that actually says if we don't reach above 10 psi within 5 seconds, we're going to shut down. So that's that line. The next line to look at is number 6. This is tied into the debounce timer, which is really that time delay on a call, and that will bring in an incoming water solenoid valve. And then here's another series of rungs through here that actually start and stop the individual solenoid valves. If you take a look at line 7 here, we've got this debounce timer, this time delay on. Here brings in solenoid number 1, or toggle switch number 1. Toggle switch happens to be toggle switch 1 takes care of solenoids 1, 2, and 3 on an override situation. But in the solenoid bit from a user interface brings in solenoid number 1. The same is true for solenoid 2, solenoid 3, and again toggle switch 1, 2, and 3. As soon as we get down here to solenoid 4, we've got toggle switch number 2, 5, solenoid 5, solenoid 6, toggle switch number 2, bringing on the different water solenoids. This is actually an output, dry contact output of the controller, which actually closes a set of contacts that does turn on the individual solenoids. We go on a little further, and this is actually the pump start delay. There's a little half-second delay in there. Time base is hundredths of a second, counts up to 50, so there's a little half-second delay. And it closes this T40 DN, and when this DN closes here, it actually does send a signal out. This is a set of contacts in the controller that send a signal to the variable frequency drive to actually start and run. And then this is another bit internal to the controller that says that the system is running. This bit will be used later on in the program. Actually, you can see it right down here to monitor some more control. So once the system starts and the command is given for the VFD to run, the VFD starts to ramp up, and that ramp up is caused by not meeting the pressure setting that it's set to run to. So it ramps up. Pressure setting on this particular package is 170 psi, so it starts to ramp up to meet that 170 psi. But this line 15 here is actually a low pressure cutout on the high pressure side, on the misting side. It's set at 120 psi, and actually this, when the system was running, it was running right at 170 psi, so this was greater than that, and it met its objective. So there's other logic here. If it didn't, if it was below 120 psi, it would shut the system down. So this next line, line 16, is a time to get up to normal operating pressure. So this is set at 10 seconds, and it waits, it monitors the incoming pressure through this system running command, and if it doesn't get up to normal operating pressure within 10 seconds, it will shut down the pump. And then this next line is a loss of pressure. If we do come to the point where we get to normal operating pressure, then another timer is in here to say, okay, if we ever lose pressure, like if we have a leak in the system, it is set at 40 seconds. That says, okay, if we go under 120 psi for 40 seconds, it will shut the system down. And then this line 18 down here is actually a control point to actually shut the system down. So this is a control point where if we have a loss of pressure, low input pressure, it will actually count this counter up one notch. Here's the counter, preset at 1. If it goes to 1, it energizes C501, excuse me, C50 energizes this DN bit, and that goes and ties up to, well, it's not there. Here it is right here. And here is where it's getting a little complex and it's hard to explain it all. Let's go back to line 18. Okay, so this is part of the shutdown circuitry. Let's go to the next line, line 19. Line 19 is actually the reset circuit. If we ever have a if it does go down on any of its monitoring set points, the way to reset it is to either reset a toggle switch or completely shut off all the calls for mist, or actually recycle the power in the system. Any one of those three will actually reset this bit here, which will reset this counter, and then it'll try again. It'll actually start from scratch. We go on to line 20 here is where we start to monitor. These are scale with parameters. These are actually monitoring the pressure transmitters themselves. This is where the pressure transmitter actually comes in and brings in data. And this input data is coming through this channel, we'll say in the controller, and it has a range of information. These values, what we're doing is we're scaling it to actual values that we understand, which is 4 to 20 milliamps, and the output goes to another data register at N7-5, and this 72 means it's actually at 7.2 milliamps at that particular time. Here's the same input register. You can see up here we've got I10, I'll call it. Here's also Y10. What we're doing here is converting it to PSI, so we really know what's going on here. So this particular scale from 3147 to 1580 corresponds to 0 to 500 psi. That is the range of the pressure transducer itself, and at that particular moment that I saved the program, it was at a 7,448, was the engineering value, and that converted that to 170 psi. So that is the output pressure. This is actually where you actually set the pressure. Why the system is running, you can go in here and double click on this and set it at 170, 180, whatever you want, and it will take that information and put it into this register here, which I'll show you later, and try to control the unit at 170 psi. Then this one actually is output pressure monitoring. Now this is actually input pressure monitoring. This should say input. I'm not going to change that now, but this is input pressure. So the same as what we went through before, and you can see that there is a value of 4728, 4 to 20 milliamp circuit, 6 milliamps is what it is, but then here is the pressure itself, 4728 out of a scale of 3147 to 15.8. The actual transducer itself is 0 to 100 psi. That correlates to 12 psi on the input. So 12 psi on the input. The next line, this is actually the PID loop, or this is what controls the variable frequency drive itself. This is the information that actually is sent to the variable frequency drive. It gets its information from N6, which is this output right here, 170 psi. Control variable of N710. That information is the output, which goes to this scale with parameters, and then that sends it out to an output analog signal, 4 to 20 milliamp signal on 0:1.0, which is the signal to the variable frequency drive to raise or lower the speed. So that's how that loop works, but there is this setup screen. Looks like I can't get at it right now. Huh, interesting. Well, there's another way to look at it. Alright, here it is. This is the picture I took of it. And this is the PDI setup loop and some values that had to go in it to get it to control the pump properly. Key to them is these first three here, the gain, reset, and actually the loop update also is key. And these are the actual input values. You can see it's set at 170. When I took this snapshot, it was actually controlling at 169. And then this is the error factor here that actually slows the speed down, or the motor, or speeds it back up again. That's that. So these move instructions, this is kind of just more information for the programmer. It is engineering units that are converted here. This again, I went over this. This is the output to control the pump. You can see that these two are the same. We're getting towards the end here. In fact, this is the last one. This is the pump panel monitoring temperature of the pump panel as an input. This is the input point where the wire actually lands, and this is a signal from it and a scale that the signal sees, and then this is a scale of the temperature sensor itself, -40 to 140. Of corresponds to 72 degrees. One thing we didn't see here was the shutdown circuit for the water sensor, and that's the sensor that's in the pump control panel itself that senses if there's a leak inside the panel itself, which will shut it down in a 30-second time frame. So let's go and try to find that. Alright, here it is. It's actually on line 1. There is a line 0, but it's on line 1. It was one of the last things I added, and all it has to do is kind of be tied into the shutdown circuitry to actually shut down the system. So this is the sensor input right here, where some dry contacts come into the microcontroller. They are normally closed, those contacts, and if it opens up, it starts this 30-second time delay. So there has to be water at that sensor for 30 seconds before it'll energize this DN function here, which comes up here and opens these contacts to stop the call for mist. So that's pretty heavy, but that's an overview of what this system does, and you could ask questions to get any more out of it. That'll do it for now. Talk to you later.